Hello, everybody. This is an ISCA 2026 talk. It is the talk for the first paper in session 3D microarchitecture. This paper is about Dorado, a clustered hardware cache coherence for 1,000+ cores. This is work done at the University of Illinois and at Intel. My name is Josep Torrellas. I'm a professor of computer science at the University of Illinois, Urbana-Champaign. Let's start by pointing out that data center processors continue to grow in core count. The biggest AMD processor now has 192 cores. The Intel Clearwater Forest has 288 cores, and the Ampere one, Aurora, which has been announced already, has 512 cores. These processors support directory-based hardware cache coherence because they want to do general purpose work and therefore run graph analytics applications, in-memory key value stores, scientific computations, ML inference, and so on. We may soon see processors to scale up to 1,000 cores per processor. Directory-based hardware cache coherence is the coherence that they use in these processors use. In this case, the directory is distributed in slices, and each memory line has a home directory slice. For example, in this case, I have a machine with 2 slices. In each slice, I have the directory with its sharers for each line, plus the last level cache. And suppose here that this processor here wants to issue a request for a line whose home is in this second slice. So it issues the request to the directory checks the sharers. It turns out that another processor has the data dirty in its cache. That processor writes back the line, and the line is forwarded. There are 2 main sources of overhead for large-scale directory protocols. The first one is the long latency and traffic induced by coherence transactions. You can see here that if this slice happens to be very far away in the package of the server, there's a huge latency to go to the directory and check and do all this long transaction. The second is the fact that as we increase the number of cores more and more, the directory storage required to track the data shares increases. So for example, this is a typical directory entry. We're going to have a set of pointers that point to the sharers of this line, plus some extra bits. So these are the 2 main overheads of directory protocols. How do we address these problems? There has been a lot of work in this area, and the paper has a taxonomy of the work in multiple that classifies the work in multiple dimensions. What do we do in this paper? We focus on the following. For the latency and traffic problem, we focus on enabling clusters of cores so that the cores in a cluster can mostly operate on shared lines locally without requiring remote accesses, hence cutting down on the latency and traffic. Second, in terms of storage, we know that most lines are not widely shared. So as people in the past have done, designs in the past, we use few pointers per entry. But we still need to support many sharer lines that have many sharers potentially. Again, there's been quite a bit of work in this area, and we will compare against past designs. The contribution of this paper is as follows. We propose Dorado, which is a new directory-based protocol for 1,000+ cores that exploits clusters. It introduces 3 innovations. The first one is 2-level homes, TLH. The idea is that each line, in addition to having its global home, as current protocols, it has multiple temporary homes to satisfy as many transactions as possibly locally within a cluster. So this is a case of 3 clusters. The one in the center is the home, and we have a processor in cluster 1 that wants to access this line. Conventionally, it would have to go to the home that is remote. What we want is to have a temporary home in the local cluster so that when the core accesses the line, it can satisfy it locally here. The second contribution is what we call dynamic apportioning. The issue here is that because now we're going to have temporary homes and global homes, the pointers to the sharers of a line now may be of different types. We may point to a core if it's local, or we may point to a cluster if it's a remote sharer. So the directory structure will have to have pointers of different types, a pointer to a core and a pointer to a cluster. That varies with time. Sometimes, depending on the locality of the program, we'll have more local pointers to cores, other times pointers to clusters. With dynamic apportioning, the idea is that we don't have different data structures for the different types of pointers. Instead, we have a single hardware structure for the directory, and the types of pointers fight it out for space. And the third is set overflow, which is a technique for the directory to support many sharer lines. The design here is that you have directory entries that correspond to lines that want a lot of sharers. So we're going to have a directory entry dynamically growing by grabbing and then releasing pointers within the same directory set. So sometimes we're going to see we're going to have 6 sharers, other times we're going to grow, other times we're going to decrease. So these are the 3 contributions of this paper. Let's go over each one at a time. The machine that we're going to be looking at is a machine with 1,024 cores, organized in 32 clusters. This box here is a cluster, and each cluster has 32 processors, 32 cores. And each of the cores has a slice of the directory. So that means that we have 1,024 directory slices spread over the whole 1,024 core machine. Let's start with the 2-level homes. Let's look at its concept. The idea is as follows. The physical address of a line determines its global home cluster. So in this case, suppose that by the address, we know that the global home of this line is this cluster, and in fact, a directory lies within that cluster. However, when a core accesses a line whose global home is remote in a different cluster, Dorado creates a temporary home in the local cluster. So in this case, this cluster here also has a temporary home for this line, and this other cluster here has a temporary home for this line. The entry remains in the local directory slice, the temporary homes remain in the local directory slices for as long as it's not evicted. And a line can have multiple temporary homes, as we see here, if multiple clusters are concurrently accessing the line. And the directory entries of a line in the global home and in the temporary homes are always consistent. Let's see how it operates. Temporary homes, the goal is to reduce access latency and bandwidth. So suppose here we have 2 clusters. The one on the right side has the global home for the line. And the one on the left is a cluster where you have a core that hopes to create a temporary home for this line locally. This core issues a read request. It accesses the local directory with the hope of finding a temporary home for this line, but it doesn't have it. So then the protocol sends a request to the global home, gets the line, and it also creates a temporary home for this line here before providing the line to the requester. The global home is always the serialization point of coherence transactions to the line, and that eliminates inconsistency in the protocol. Suppose we have here 3 clusters. The one in the center is the global home for the line. The one on the left is the one that we just created. The reading of a line in the previous example created this temporary home. And then there is a third or a second temporary home in a different cluster. Now suppose that the processor attempts to write the line. It goes to the local, the temporary directory, and it says that you don't have permissions to write here. You need to check with the global home. So the protocol sends a request to the global home, which then will invalidate the entries in the global home, send another message to the temporary home, the second temporary home, invalidating all the cores there, responding, the global home directory is updated, and then the line is provided to the local cluster, and the temporary home in this local cluster is also updated to say that now you have it dirty here. Note that a transaction like this one that may change the state of the global home, the home in the center, cannot lock any resource in the temporary home, in this cluster here, until the transaction has been able to reach the home and lock the global home. Only then, after it has locked the entry in the global home, it can start locking other things, because everything is serialized in the global home. The second idea is dynamic apportioning. The idea here is as follows. Because now we have global homes and temporary homes, we're going to have different types of pointers. I have here two clusters, and in this cluster I have 3 directory entries for 3 different lines and 2 cores here. The first type of pointer is the green pointer. The idea is that this is for data where this cluster here is the global home for this data. And in addition, the sharer core, the one that wants the data, is also local. So local in terms of global home and local as the sharer. This is a green pointer. The contents is a core ID, and the home is global. The second type is a yellow pointer. A yellow pointer is one where this cluster is still the global home of the data, but the sharer is a remote cluster, is in a remote cluster. Okay, so it has to point to a remote cluster. So the contents of this pointer is a cluster ID, and this is a global entry, a global home for this line. And finally, there is the red pointer. The red pointer is the case where this cluster is not the global home of the data. It's a temporary home, but the sharer here is local, in which case we have the pointer that points to has a core ID, but the home is a temporary home. These are the 3 types of directory informations. So one approach would be to have different hardware structures for each of the pointers and for each of the global and temporary homes. Instead, with dynamic apportioning, the idea is that we have a single structure. Specifically, a global directory entry can have both pointers of type 1 and 2. And these are not specified as 10% green and 10% or 90% yellow. Instead, the numbers of each vary dynamically depending on the locality of the program. Programs that have poor locality will have a lot of yellow pointers. Programs that have a good locality will have green pointers. Also, in the same directory slice, we're going to have both a combination of global and temporary directory entries. So in this case, we're going to have this red pointer that corresponds to another line whose home here is only temporary. The combination or the fraction of global and temporary homes depends on the locality, again, of the program. If you have good locality to start with, maybe most are global. So dynamic apportioning saves space by dynamically sharing the hardware based on the application needs. And the third technique is an efficient way to support many shared directory entries. And this is what we call set overflow. The idea is as follows. The goal is to dynamically support many sharers for a few directory entries. So we're going to keep a group of additional sharer pointers per directory set. We call this the pointer space. So here's the example. So what we see here is a 3-way directory. So this is a directory slice with 3 ways, right? And for each of them, we're going to have, so this corresponds to a line. Let's take a set. This is a set, right? This corresponds to a line that has a pointer, one sharer only, and this one has only a sharer, and this one has only a sharer. Well, since we can only support, say, 2 sharers per line, we're going to have this pointer space that has extra pointers that can be shared by all the lines, all the directory entries in this set. Okay? So when one of the ways runs out of pointers, then we're going to set this O bit, overflow bit, to 1 and take some entries from the pointer space. So for example, in this case, suppose that after running for a while, this way wanted 4 sharers. Because it only has 2 pointers here, it will set the overflow bit to 1 and take 2 pointers from the pointer space. And this one here also overflowed and took 1 entry from here. So this fine-grained reassignment of the pointer space pointers to entries of the set is what makes this different from past designs. And the accesses to this pointer space are never in the critical path except in one case. They're in the critical path only when you receive a write and you have to invalidate all the sharers and the line has a 1 bit here, then you gotta have hardware that goes and checks these pointers here and sends invalidations. Let me give a few examples of the operation of the Dorado scalable directory protocol. First, let's look at the write miss to data that is unmodified, where the local cluster has a temporary home. So this is the example. We have 3 clusters, as we saw before. The one in the center is the global home. These 2 clusters have temporary homes for the line. Circles here are processors or caches. And this line that we want is being shared by a processor in the local cluster, a core in the home cluster, and a core in a third cluster. All of them in state shared. You can see that the home has a green pointer to point to this one, 2 yellow pointers that point to this cluster and this cluster. And in each of these clusters, we have a red pointer that says, I have a local share for data whose global home is remote. Red pointer here, red pointer here. When this one wants to write, what it has to do first is goes, checks the temporary home and directory and sees that it cannot write without invalidating everybody. So it will send an invalidation to the local share and also to the home. As the local sharer acknowledges, you're going to remove the entry here. Remember, we cannot hold this. We have to remove the entry. A request is sent to the global home cluster, which sends invalidations to any local sharer, and also sends a request to the third cluster. The local sharer here acknowledges and removes the sharer. Here, send an invalidation to the local sharer, which acknowledges, removes the entry, sends an acknowledgement back to the home, remove the sharer, and then the global directory here updates this to say, now the line is dirty in that local cluster. The line is sent, a pointer is created, and the line is passed to the requester. Let's look at another example. Suppose that now we have a read miss to modify data where the local cluster has a temporary home. So continuing with the example that we saw before, this was the core that wrote, became dirty, and created this pointer here, which is a red pointer. And the home contains a yellow pointer saying, this cluster here has the line in state dirty. And now suppose that this core wants to read the line. It goes to the temporary home, and it sees that the line is locally dirty. Why not read it from here? So it issues a request to the owner, say, give me the data. This one provides the line and changes to modified shared state. What this means is that the line that it has in the cache is coherent with the one in the local directory last level cache, but it is not coherent with what the home has. The home doesn't have it because it's dirty here. The line is provided to the reader, and both keep 2 pointers, obviously, 2 red pointers, and both become modified shared, which means that now they can read and write the line without informing the home, because the home doesn't care what's going on in that cluster as long as it knows that it is dirty there. So there is no need to inform the global directory when the local caches read and write data in a state dirty or modified share. Now, the paper has the protocol described in gory detail, all the transactions that can occur and what all the changes are. So I encourage you to read the paper and you'll see the whole coherence protocol. We evaluated this through simulations of a machine of 1,000 cores, 124 cores, organized, as I showed before, with 32 clusters of 32 cores each. And we run a lot of benchmarks, a lot of workloads from graphs, informatics, data analytics, key value stores, and so on. One of the data that we show in the paper is the speed up of a variety of directory-based coherence protocols that have the same directory area. So I'm going to show you 5 protocols that have the same directory area. The first one is dir2b, which is a vanilla flat directory protocol. Flat means that it's not clustered. It's a conventional non-clustered protocol. Because it has 1,000 cores, each pointer has to be 10 bits, and we only have 2 pointers per directory entry. On top of this one, we add TLH, the 2-level homes. Because now some of the pointers point to clusters, we can reduce the pointer size. And therefore, we can have each pointer to be 5 bits only. And that means we can have 4 pointers per directory entry. On top of this, we add the dynamic apportioning. We call this TLH dir3b dynamicity. Now, because we have to separate, now in the previous one, here we had to have specific sizes of yellow pointers and specific size of green pointers. Now we're going to have a single data structure, hardware structure, and we have the pointers fighting out for space. Because of that, we have to mark the pointers with an extra bit that says whether I'm a core pointer or a cluster pointer. And therefore, we increase the size and we have fewer pointers per directory entry, only 3. And finally, on top of this, we add set overflow, and that is Dorado. In this case, we add 12 pointers, extra pointers in the pointer space per set, and that reduces the amount of pointers per entry to 2 pointers, as I showed before. And finally, we have an upper bound, which is to take this one here, TLH dir3b dynamicity, and add a full bit vector for every entry, 36 pointers per entry. In this case, we cover the whole machine. We never experience lack of information, but this is very costly in space. So what we have here is the speed up of the 5 different protocols for the different applications and the mean, and the bars are normalized to dir2b. So in each of the applications and in the mean, the first bar, dir2b, is 1, and then we have all the different bars. So higher here is better, which means higher speed ups. So what we can see here is that for Dorado, each of the 3 contributions, 2-level homes, this one here, dynamicity, and the set overflow, each of them is effective on every application. For some applications, the gains are very small, for others are very large, but in all cases, is a positive effect, never a negative. And if we look at the mean, we see that Dorado attains an average speed up of 1.3x over the dir2b and is within 1% of the upper bound. So this is a good result. We also compare multiple many-share designs that have the same directory area. So we started with the dir2b as usual, which is the vanilla flat directory protocol. We add both two-level homes and dynamic apportioning, to be fair. And then on top of this, we're going to add three different designs. First, we're going to add SCD, which was proposed by Sanchez. Or we will add way combining, which was proposed by Titus Hill. Or we will have Dorado, which adds set overflow. So the baseline is the same, this one here, and we add each of the different proposals, two different proposals and our proposal. And here is the overall speed up for the different applications and the mean, again, as usual, normalized to dir2b. So we can see that adding the two homes and adding the dynamicity, we improve the speed up quite a bit. And then on top of that, we see the effects of the many-share line designs. What we can see is that both SCD and WAC produce modest speedups. SCD because it incurs directory conflicts. WAC because it is relatively inflexible. It needs a free line, a free directory entry to grab all the pointers from that entry. Set overflow, which is Dorado, gets a speedup of 10.5% over TLH dir3b DIN, thanks to this fine-grained assignment of the extra sharer pointers to multiple lines in the set. So to conclude, Dorado is a new cluster-based cache coherence protocol for 1,000+ cores. It introduces three techniques: two-level homes, dynamic apportioning, and set overflow. It attains an average speedup of 1.36x over a same-area limited pointer protocol, and stays within 1% of the performance of a full bit vector protocol while using much less directory storage, 2.75x less directory storage. Thank you very much. That concludes the talk.